Today I will solve IMO 2019 problem 3. This problem was about the graph theory. We are given 2019 users. There we know that 1010 users have exactly 1009 friends and 1009 users have exactly 1010 friends. And we can make movements like this one if we take any point A and its two neighbors B and C, which are not connected to each other. We can close the relationship between A and B, and we can make friends B and C. And our aim is to make these movements until we get all of the users have exactly at most one friends. And we need to prove this one, that until finitely many moves we can get this situation. At first notice that nothing will be changed with the parity of the degrees of each vertex in modulo 2, because if we look at the degree of A, it will decrease by 2. Degree of B and degree of C, both of these are unchanged because before they are connected to A and now they are connected to each other. And also after each move, number of edges decreases by 1. So we can see that this process will finish at some moment. And how can we use the fact that 1010 users has exactly 1009 friends and another one has 1010 friends? This is very awkward awkward statement. But from the very experienced contestants can notice that this means that our initial graph must be connected. And let's assume that these are not connected and take any points D and D. So we can't find a path from D to E. If D is connected to E, then we can find path. That's clear. And now let's discuss all of the neighbors of D. D will have at least 1009 neighbors. And similarly can be said for E. It will have 1009 neighbors. And if we count the total number of vertex in the graph, we will get 2 times 1009 plus 2. This 2 is because of E and D. So in total, we get that total number of vertices must be greater or equal to 2020. And this is clearly contradiction because in total we have 2019. So we have proved that there will be always intersection of these two sets, edge set of E and edge set of D. So we can find the path from D to E. Like some point will be their intersection. Call this K. And now we will prove that after taking the initial graph, which was connected, after each operation it will be also connected. At first notice that in the initial graph we can't have a clique. Clique means that all of the vertices are connected to each other, because we know that some of the vertices has degree at least exactly 1009 and another vertices has degree 1010. So initial graph can't be clique. And now discuss the case then. If we are given a tree, how can we solve this case? Our aim will be to make operations such that we will finish up the connected graph who will be a tree. So we will not have any cycle. What can be done in this case? If we look at this tree, we need to take from the leaves. We need to take operations from the leaves. Call this point A and B and C. We can see that A, B, C can be A is connected to B and A is connected to C. So we can make the operation and we'll make B and C connected to each other, and these two bonds will be cut. A can't be connected to C and A can't be connected to B after this operation. Now we will continue such kind of process for each leaves. Then A will become our new leaf and do the same operation once again. But what can be done if the vertex has only one neighbor? In this case, this vertex will be out of the tree and call this one D, E, and K. If we make the operation for D, E, K, E will be connected to K, and DK and ED edges will be cut off. So D will be a new island. So we can make these moves until we get all of them must be connected to the initial root tree, root vertex. And after finitely many operations, we can get there. We will have at most one friend vertices, like C and B will have exactly one friend, and points like D will have no friends. So if we do the same operation for every leaf, we can get back to the R, and for R, we know that R is connected to some number of elements. So we can discuss this, called R1 and R2. They are not connected to each other, but after the operation, R1 and R2 edges will be cut off, and R1 and R2 will be connected to each other, and similarly for every other two vertices. And if the number of its neighbors is odd, R will be connected to RK, and we will finish the process. So in this step, we get all of the vertices has at most one neighbor. And now look at why can we get a tree after these operations. Now let's discuss the cycle, the smallest cycle in our initial graph G. Let's assume that its size is not free, and then assume that this is not Clique. Whole graph will not be this one. So now let's take any point out of this cycle. Call this C. What can be done about C? Call these points A1, A2, A3, and A6. In our case, it was 6. C must be connected to at least one of these vertices. So, or we can see that from each of these vertices, or there will exist one vertex from which there comes out at least one edge, and call this new edge D. What can be done in this case? If D is not connected to any of them, then we can split this cycle, like if D is not connected to A5, A3, we can make the operation for A2, A1, A2, A3, and these three edges will give us D will be connected to A3, and nothing will be changed. Our new graph will be also connected, and our cycle has been cut off, so we will not have any new cycle. We will do the same operation for the bigger cycle, and so on until we get cut off all cycles. And at this step, if we are given a triangle when we cannot make such moves, now let's discuss the maximum size clique. All of them are connected to each other. In this step, we need to find another vertex. In the similar logic, there will be existed another vertex which will be connected to at least one of these vertices. Call this C. C is connected to A. Clearly, C can't be connected to all of these vertices because we have taken this, call this G prime must be the maximum size clique in G. So there will exist another vertex, maybe B here. There we don't have any edge between C and B. And if we write if we make this operation for A, C, and B, we will see that A will be cut off from the graph, AC will be cancelled, cut off, and also AB, but C will be connected to B. So the size of G prime will decrease. And we can make this operation until we get the triangle. And for triangles, if we know that this is new point C, like A, B, D, if A was connected to C and B was not connected to C, then we can make this operation like B will be connected to D and AB and AC will be cut off. So our new graph will be also connected, but the size of the edges, the number of the edges will decrease by 1. And clearly we can continue this process until we get a graph which will not have any cycles and any cliques. And now use the fact that in the initial graph we are given vertices who has odd degrees. So after these operations, I have already seen that parity of the degrees modulo 2 does not change. So in the end, it will have also 1 edges. But now let's consider a cycle. Why can't we have a cycle who has all of the vertices? And why is this impossible? Because in a cycle, we know that all of the vertices has degree of 2. Degree of AV must be 2. And clearly this is impossible because in the beginning we are given vertices who has odd degrees. And after these operations, their parity modulo 2 will not be changed, and this is impossible. So when I have discussed the smallest cycle and then choose the point which was outside the cycle, this was very good idea, because such point will be existed always because of the statement that there will not be a complete cycle, and this will also cut off the cycle and cut off this small cycle, and we will get the similar structure to the tree. So this was not too awkward idea. If we look at carefully to the problem statement, we can see that this problem can be solved without the given that every vertex has exactly 1009 and 1010 vertices. The main idea was that if we have at least one vertex who has odd degrees and they have more than 1009 edges, then we can always solve this problem. So if you got any questions about this problem or solution, please write in the comments and I will try to explain this to you. And don't forget to like and subscribe.